Hello, I'm Dr. Daniel Wilson, and welcome to Lawrence Berkeley National Laboratory's instructional video series on laboratory testing of cookstoves. Today's lesson will be on the design of a particle sampling system for your cookstove lab. After watching this lesson, your lab will be able to design a probe for gravimetric aerosol sampling, select an aerosol size separator, choose the correct filter size and holder for your laboratory, and reliably control the flow rate through your size separator and filter. The purpose of a gravimetric sampling system is to deposit aerosols of a known particle size range and from a known volume of air onto a filter. By comparing the difference in mass between a clean filter and a filter loaded with aerosol, we can calculate the average aerosol concentration in the air that passed through the filter. The most common aerosol metric of interest is called PM2.5. PM2.5 refers to the mass of aerosols whose diameter is smaller than 2.5 microns. We are concerned with particles smaller than 2.5 microns because their health effects have been shown to be more harmful than larger aerosols. Often, PM2.5 is expressed as a volumetric mass concentration with units of micrograms per cubic meter. To visualize what this means, imagine 1 cubic meter of air. Then imagine all of the aerosol particles that occupy that space. If we remove all the particles larger than 2.5 microns, then weigh the remaining small particles, we would find the total mass concentration of PM2.5 per cubic meter of air. In this example, if we imagine that the fine aerosols that came from 1 cubic meter of air weighed 200 micrograms, our PM2.5 concentration would be 200 micrograms per cubic meter. While PM2.5 is typically discussed in terms of mass per unit volume of air, in cookstove testing we will also discuss PM2.5 in terms of mass of aerosol per mass of fuel burned, or mass of aerosol per unit energy delivered to the pot. A well-designed gravimetric sampling system performs the job of removing large particles from the emission stream, then deposits the remaining small particles onto a sample filter. Your gravimetric PM2.5 sampling system will draw emissions from your dilution tunnel at the sampling port. As with sampling gases, a probe is needed to draw emissions from the dilution tunnel into the gravimetric sampling train. However, unlike sampling gases, the design of the probe is critical to ensuring a quality aerosol sample. Your emissions may be traveling quickly through your dilution tunnel, and so it is important that your probe draw in emissions at roughly the same velocity that they are moving through the tunnel. This is called an isokinetic sample. Isokinetic sampling helps ensure that the sampled emissions are not biased towards heavier particles, which tend to be overrepresented if the probe's flow is much slower than the emission stream. Isokinetic sampling also prevents overrepresentation of smaller particles, which can be overrepresented if the probe's flow is much faster than the emission stream. Although there is some debate about the necessity of isokinetic sampling of cookstove emissions, we recommend that you follow the best practices and design your probe for isokinetic flow. To match the velocity in your probe to the velocity in the dilution tunnel, simply compare the ratios of volumetric flow rate and area for the dilution tunnel and probe. This equation can be rearranged to find that the isokinetic inner diameter of the probe is equal to the dilution tunnel diameter multiplied by the root of the ratio of probe flow rate to tunnel flow rate. Using LBNL's flow rates and dilution tunnel diameter, you can see that the ideal inner diameter for our probe is 14 millimeters. The opening of this probe should face upstream of the flow, and we recommend that the probe have at least 10 probe diameters facing upstream before adding any gentle bends so that the probe can exit through the sampling port. We connect our sampling probe to the rest of the gravimetric sampling system using a length of flexible conductive tubing. It is critical that all components of the gravimetric sampling system, from the probe down to the filter holder, be electrically conductive and connected to earth ground. This is to avoid the accumulation of static charge, which could cause aerosol particles to stick to the walls of sampling tubes, causing significant errors. The conductive tubing connects the sampling probe to the next important piece of hardware in the gravimetric system, the aerosol size separator. This is the device that will remove particles larger than 2.5 microns from your sample. The two most common size separator designs on the market are cyclones and impactors, but we highly prefer cyclones because of their ease of maintenance and dependability when exposed to very high emission concentrations for long periods of time. Cyclones spin your sample emissions very quickly, causing large particles to fall out of the emission stream. These large particles, which often contain flecks of ash, collect in a grit pot and are emptied daily. Cyclones must be operated at their specified flow rate in order to remove particles above their rated size. If a cyclone is run without sufficient flow, its cutoff size will be higher than 2.5 microns. And if the cyclone is run with too much flow, particles less than 2.5 microns will be removed from the emission stream. We will discuss how to maintain a constant flow rate through the cyclone later in this video. At the outflow of the cyclone, your sample should only contain particles smaller than 2.5 microns. They are now ready for collection on a filter. As the aerosol stream passes through the filter, which is contained inside of a filter holder, it deposits more than 99% of the particles. The deposits of these accumulated particles are what will be weighed later to determine your Cookstoves PM2.5 emissions. The process of weighing filters before and after testing is critical to the operation of a high-quality cookstove testing facility, and so for that reason, we've dedicated an entire future video just to that topic. The most important design consideration when selecting a filter holder is to consider your filter's diameter. The larger the diameter of your filter, the more aerosol can be loaded on the filter before it clogs and causes errors in the flow rate. Please refer to your filter manufacturer's recommendations for maximum loading, which will typically be expressed in terms of mass per filter area. A larger total deposited aerosol mass may be useful if your laboratory does not have an analytical balance with very fine resolution. Our lab uses 47 mm diameter filters with a duct flow rate of 325 cubic meters per hour and a gravimetric system flow rate of 16.7 liters per minute. We find that, with this combination, we can perform tests on a wide variety of stoves, accumulating total aerosol deposits of between 100 micrograms and several milligrams. If your lab uses a significantly lower duct flow rate than ours, tests extremely dirty stoves, or cannot afford a balance accurate and precise to roughly plus or minus 10 micrograms, you may need to use larger diameter filters. At the exit of the filter holder, the air will be particle-free. It is at this location that we want to control the flow rate through the gravimetric sampling system. We do not want to place any flow control devices upstream of the filter because any restriction in the gravimetric sampling train is likely to cause unwanted deposition of particles. For flow control, we highly recommend using a critical orifice. A critical orifice is nothing more than a precision-drilled hole. Our critical orifice is designed to thread into the barb at the outlet of our filter holder. When a critical vacuum pressure is reached downstream of the critical orifice, supersonic flow will pass through the orifice. In this shot, you can see a pressure gauge monitoring the downstream pressure of our critical orifice, with the critical pressure marked with red tape. Once the critical pressure is reached, the flow through the orifice is supersonic and the flow is choked. Choked flow is very convenient because, no matter how much more vacuum is applied, the mass flow rate of air through the orifice will remain constant. In other words, as long as your pump can supply more than the orifice's critical vacuum pressure, you can be guaranteed a constant flow rate through the orifice. This vacuum side flow control is essential for ensuring the constant flow rate that your aerosol size separator needs. Downstream of our critical orifice, we have a ball valve. This helps us easily cut off flow through our filter to precisely time the start and stop of tests. You can also see that our system employs an optional filter bypass system. This is because our particular vacuum pump is not designed to pump zero flow, So when our filter flow is shut off, we open this bypass to protect the pump from overheating. With your gravimetric sampling system in place, you will be able to calculate the total emissions of PM2.5 emitted by your cook stove during a test. Using the mass of PM2.5 deposited on the filter, and assuming that the gravimetric system's flow rate is very small compared to the flow rate through the duct, we can use a simple equation to calculate the total emissions from the cook stove. Total PM2.5 mass emissions from the cook stove is simply PM2.5 mass on the filter multiplied by the ratio of average dilution tunnel flow and gravimetric system flow during the test. Rearranging this equation, you can estimate total aerosol deposited on your filter for a given total cookstove emission per test phase. As discussed previously, you can use this estimate to select the appropriate filter diameter for your lab. In conclusion, your gravimetric sampling system should have a probe that samples isokinetically from your duct. It should be electrically conductive throughout and connected to earth ground. It should incorporate a size separator to remove particles larger than 2.5 microns, and it should utilize appropriately sized filters for your expected loadings and microbalance specifications. Finally, your system should have a well-controlled flow rate, preferably using a critical orifice monitored by a pressure gauge. Thank you. I'm Dr. Daniel Wilson from Lawrence Berkeley National Lab. Please join us for our next instructional video on laboratory testing of cookstoves.